stomach, and it is a temporary storage tank that starts the chemical breakdown process, particularly of proteins. It converts the bolus of food into a different substance, a more paste-like substance that we're going to refer to as chyme while it's in the stomach. Stomach has about a 50 milliliter volume. However, it can be expanded to as much as 4 liters. When it's empty, there are rough edges on it called folds that are called rugae. It's divided into 4 basic parts: the cardiac part, or cardia, which surrounds the cardial orifice; a fundus, which is a dome-shaped region just beneath the diaphragm. The body would be the mid portion, and the pyloric part, the other end, is wider, more superior in portion of the pyloric region, the antrum, into the pyloric canal that terminates in the pylorus, and there's a sphincter there, which is continuous with the duodenum. The pyloric valve, or pyloric sphincter, is going to control the emptying of the stomach. So we have the esophagus coming in, cardiac region, the fundus region, the body down to the pyloric region. We have a greater curvature on this side and a lesser curvature on the inside. So that greater curvature is on the lateral surface. The lesser curvature is on the medial surface. There are mesenteries that extend from the curvatures to tether the stomach to the other digestive organs. The lesser omentum runs from the lesser curvature to the liver, while the greater omentum drapes inferiorly from the greater curvature over the intestines, the spleen, and the transverse colon, where it will blend with the mesocolon, which is mesentery that anchors the large intestines to the abdominal wall. There are fat deposits in this, and there are also lymph nodes. The autonomic nervous system supplies the stomach. There are sympathetic fibers from the thoracic splenic nerves that are relayed through the celiac plexus, and parasympathetic fibers supplied by the vagus nerve. Its blood supply comes from the celiac trunk, gastric and splenic branches, and its veins are part of the hepatic portal system. Microscopically, the stomach has the regular 4 tunics. The muscularis and the mucosa are modified in the stomach. The muscularis externa has a circular and longitudinal smooth muscle layer, as well as a third layer which runs diagonally, so it is an oblique layer. So together, those smooth muscles allow the stomach to churn, mix, move chyme, really beat up on it, pummel it, and that increases the physical breakdown and rammed it into the small intestines in little squirts. The mucosal layer is modified. It consists of a simple columnar epithelium entirely composed of mucus cells. They secrete 2 layers of an alkaline mucus. That surface layer traps bicarbonate-rich fluids beneath it. It is dotted with gastric pits, which lead into gastric glands, and those gastric glands are going to produce gastric juice, which are the digestive materials. So here we have the surface with little look like holes in it. Those are the pits, and those pits go down into here where we have the glands. Those glands are in the fundus in the body, produce most of the gastric juice. They include secretory cells. There are mucous neck cells, parietal cells, chief cells, and enteroendocrine cells. We have the mucus cells, mucous neck cells, parietal cells below those, and interspersed with them, chief cells below that, and enteroendocrine cells interspersed in the lower parts with those. So the mucous neck cells secrete a thin acidic mucus. We don't really know what its function is. Most of the mucus in the stomach is basic mucus to counteract the acidity. Parietal cells secrete hydrochloric acid, which has a pH around 2, and it denatures proteins, unfolds them. It activates pepsin, an enzyme, and it breaks down cell walls in plants and kills most bacteria. The parietal cells also secrete a substance called intrinsic factor, An intrinsic factor is a glycoprotein that is required for you to be able to absorb vitamin B12 later on in the small intestines. Chief cells secrete pepsinogen and lipases. Pepsinogen is an inactive enzyme. It's activated to become pepsin when it's broken down by hydrochloric acid or by another pepsin molecule. So this has a positive feedback mechanism. And pepsin breaks down amino acids. Lipases digest lipids, and about 15% of lipids get broken down to some degree in by the secretions of chief cells. The enteroendocrine cells secrete chemical messengers into the lamina propria. Some act as paracrines, so they act locally. That would be serotonin and histamine. Others act as hormones, as well as it has some paracrine function. Somatostatin and gastrin, so they have widespread effects. The mucosal barrier, as you know, inside the stomach there are very harsh digestive conditions. That means the stomach needs to be protected, because in reality the stomach is made up of the same things that you're trying to break down in your stomach. Part of that is the mucosal barrier that protects the stomach. It's created by three factors. There's a thick layer of bicarbonate-rich mucus. There are tight junctions between the epithelial cells so that the juice doesn't get through them. And damaged epithelial cells are quickly replaced by the division of stem cells. In fact, the surface cells on average are replaced every 3 to 6 days. Gastritis is an inflammation caused by anything that gets past the stomach's mucosal barrier. Peptic or gastric ulcers can cause erosions in the stomach wall. The erosion can perforate the wall, and that can lead to peritonitis and bleeding or hemorrhage. Most of the ulcers are caused by a bacterium called Helicobacter pylori or H. pylori. It can be exasperated by non-steroidal anti-inflammatory drugs such as aspirin. Here is an image of an ulcer. And here are our good friends H. pylori. This is a common cause of ulcers. If you have an ulcer, you probably have H. pylori, but just because you have H. pylori does not mean you will get an ulcer. So digestion. Digestion in the stomach includes a breakdown of food. It's a holding area for food. It delivers the chyme to the small intestines, where most of our digestion will occur and absorption will occur. It denatures proteins with hydrochloric acid, which means it unfolds them, puts them into their primary structure. Pepsin carries out enzymatic digestion of proteins. There is a milk protein called casein that's broken down by an enzyme called renin in infants, and that's why there is a curdy substance when infants regurgitate on you. Lipid-soluble alcohol and aspirin are absorbed directly into the blood from the stomach. Only stomach function that is essential to life is the secretion of that intrinsic factor so that vitamin B12 can be absorbed. But B12 is needed for red blood cells to mature. Without intrinsic factor, we develop pernicious anemia, and that has to be treated either with B12 injections or a B12 nasal spray, because you can't absorb it through the digestive tract without intrinsic factor. The gastric mucosa secretes about 3 liters of gastric juice per day. It's regulated both by neural mechanisms and hormonal mechanisms. The vagus nerve stimulates an increase in secretion, while sympathetic stimulation would decrease secretions. Gastrin, a hormone, is going to stimulate hydrochloric acid secretion by the stomach, and there is a gastrin antagonist produced by the small intestines. Gastric secretions are broken down into 3 phases. There's the cephalic or reflexive phase, the gastric phase, and the intestinal phase. And this kind of refers to what's going on in your head, what's in the stomach, and when it moves to the intestines. So that cephalic phase is a conditioned reflex triggered by anything from aroma, sight, taste, even thought. Once food hits the stomach, it lasts about 3 to 4 hours, providing 2/3 of the gastric juice released, and its distension of stretch receptors initiate the long and short reflexes. There are also chemical stimuli such as partially digested proteins, caffeine, low acidity. These things will activate the enteroendocrine G cells to secrete gastrin. The release of gastrin would then initiate hydrochloric acid release from parietal cells and activate enzyme secretion. They prod the parietal cells to secrete hydrochloric acid by binding to receptors on the parietal cells and stimulating the enteroendocrine cells to release histamine. There's a buffering action of ingested proteins causes the pH to rise. That would activate more gastrin secretion. Low pH would inhibit gastrin secretion. That would occur between meals and during the digestion as a negative feedback mechanism. So the more protein, the more hydrochloric acid secreted. That would cause a decline in pH, and that would inhibit gastrin secretion. As things move to the intestines, we get a brief stimulatory component followed by inhibition. That stimulatory process is partially digested food gets into the small intestine, causes a brief release of intestinal enteric gastrin. That encourages the gastric glands of the stomach to continue secretory activities. The stimulatory effect is brief, and it's going to be overridden by inhibitory stimuli as soon as the intestines fill. That inhibition phase, 4 factors in the duodenum that cause a decrease of gastric secretions are distension of the duodenum due to the entry of the chyme, presence of acidic chyme, presence of fatty chyme, and the presence of hypertonic chyme. The inhibitory effects protect the intestines from being overwhelmed with too much chyme or acidity. Inhibition is achieved in 2 different ways, the enterogastric reflex and enterogastromes. That reflex, the duodenum, inhibits acidic secretions in the stomach by the enteric nervous system, the short reflexes, while the sympathetic nervous system and the vagus nerve act as the long reflexes. Enterogastromes are duodenal enteroendocrine cells that release hormones that inhibit gastric secretion, and they are secretin and cholecystokinin, or CCK. So in the cephalic phase, we stimulate a lot through our cerebral cortex that food is coming, so you need to prepare by turning on the hypothalamus, the medulla oblongata, to stimulate the vagus nerve to get the stomach going. When food reaches the stomach distends, food chemicals are detected, and then long and short reflexes want more stimulation. The G cells will secrete gastrin, and the stomach secretory activity will go up until it makes its way into the intestinal, small intestine, duodenum of the small intestine. And that will give a brief spur to this, but then as the intestine fills, we hit the inhibitory events and they take it downward. And these also have cerebral, cephalic phase, gastric phase, and intestinal phase. Some of the hormones, you should go through this table. These actually 2 tables, I believe, coming up in your book. CCK, glucose-dependent insulin tropic peptide, commonly called gastric inhibitory peptide, gastrin, histamine, intestinal gastrin, motilin, secretin, serotonin, somatostatin, and vasoactive intestinal peptide. So how do we make hydrochloric acid in the stomach? The parietal cells are going to pump hydrogen ions, and that comes from carbonic acid, into the stomach lumen through a hydrogen ion potassium ATPase, which is commonly referred to as a proton pump. Remember, a hydrogen ion is a proton. So as a hydrogen ion is pumped into the stomach lumen, bicarbonate is exported back to the blood through a chlorine and bicarbonate antiporter. That results in an increase of bicarbonate in the blood leaving the stomach, and that is referred to as an alkaline tide because it has a negative charge. Chlorine is pumped out of the lumen and joins with the hydrogen ions, forming hydrochloric acid, HCl. And that is mapped out in figure 2320. When the stomach is filling, it can stretch to accommodate the incoming food, and there are two factors that allow the pressure to remain constant until you reach about 1.5 liters of food. We have receptive relaxation, which is a reflex-mediated relaxation of the smooth muscle coordinated by the swallowing center. And gastric accommodation is its intrinsic ability of that smooth muscle to exhibit a stress relaxation response, and that will enable most hollow organs to stretch without increasing tension or contractions. Gastric contractility activity is peristaltic waves move towards the pylorus. They move that way about 3 per minute. There is a basic electrical rhythm, a BER, which is set by enteric pacemaker cells. Those used to be called the cells of Cajal, after another famous anatomist, but enteric pacemaker cells is really a more descriptive functional name. Those pacemaker cells are linked by gap junctions so that as they spontaneously depolarize, the cells they are connected to and the entire muscularis contracts. Distension and gastrin will increase the force of contraction. Conditions are most vigorous and powerful near the pyloric region, and that pushes about 30 milliliters of chyme, 3 milliliters at a time spurts into the duodenum, while the other 27 milliliters is moved back into the stomach. So only thing that gets into the duodenum are liquids in very small particles, and they get there through the pyloric valve. Why is there an acute allergic reaction slide in this presentation? I don't know, but this is where I thought we were going. Peristaltic waves in the stomach. So they move forward, propulsion. We also get grinding. And finally, we get some retropropulsion as 27 milliliters is pushed back this way, but about 3 milliliters makes its way through that sphincter into the duodenum, the first part of the small intestines. The regulation of gastric emptying. Duodenum can prevent overfilling by controlling how much chyme enters into it. There are duodenal receptors that respond to stretch and chemical signals. The enterogastric reflex and enterogastrones will inhibit gastric secretions and duodenal filling. Takes about 4 hours to empty the stomach, but that can increase if there's a high fat level in the duodenum, go up to another 2 hours. While on the other side of that coin, carbohydrate-rich chyme tends to move very quickly through the duodenum. And here is an overview of the neural and hormonal factors, figure 23-22. Vomiting or emesis is caused by extreme stretching. Intestinal irritants can do it. Bacterial toxins, excessive amounts of alcohol, spicy food, some drugs. There are chemical and sensory impulses that stimulate the emetic center of the medulla. And excessive vomiting can lead to dehydration and electrolyte depletions, as well as acid-base imbalances. So fluid replacement is very important. That would take us to the liver, the gallbladder, and the pancreas, and we will pick that up in the next slideshow.